Okay, we're going to look at differentiation and integration in Unit 3 now, which is to take a lot of what we've learned from Unit 1, differentiation and integration, and under the umbrella of calculus, and extend that on. The first thing that we're going to look at is start to involve trigonometry into the process of differentiation and integration. So the first thing then, with reference to that, is going to be the differentiation of sin x and cos x. Okay. Now if we think about the curve y equals sin x, it goes up to 1 and minus 1, and it's got a period of 360 degrees. Alternatively, we could say that that's 2 pi if measuring the thing in radians, and that is y equals sin x. Now, what we're going to start to project then is what happens if we differentiate sin x. So that's something that we've not looked at before, differentiating a trigonometric term. Okay, now if we think about where on the graph of y equals sin x, where the stationary points are located, well, the stationary points are located here and here, at 90 degrees and 270 degrees, or if that was in radians, it would be pi over 2 and 3 pi over 2. Now, if I was then to look at the differentiated function, now this is now a number line for gradient, where this would be positive gradient, negative gradient, and zero gradient. So this is me kind of looking back to some of the drawn derivative stuff from Unit 1. Well, in that number line, which measures gradient, positive gradient, negative gradient, zero gradient, I know that the stationary points, the positions of zero gradient, would come at pi over 2 and 3 pi over 2. So that would need to go through there and there. Okay, now, we do know before I get to pi over 2, the curve is positive, so that would be in this area. Between pi and pi over 2, the curve is, the gradient is negative, so that would be in this area. And after 3 pi over 2, and before I get to 2 pi, the curve's going back up again, so that would be up in this area, because that would denote positive, negative, and positive gradient. Now, what I then get is this curve. Okay, and what we extract from that is that if you draw the derivative of y equals sin x, you end up getting cos x. And what we can say generally is true then, that if you've got y equals sin x, the derived function, the derivative of that is cos x, and that's been illustrated by that graph to that graph. Okay, y equals sin x, when you differentiate it, you get cos x. Now, that is in your formula sheet. So it will be given to you. The next thing that we're going to look at is what happens when you differentiate not sin x, but if you differentiate cos x. So let's have a think about that. Okay, so let's think about the graph of cos x. Okay, so that's 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, where's the stationary points in this curve? Stationary points occur here, that's a position of 0 gradient, here, and back up at 2 pi. So that's y equals cos x. So I'm now going to go after the derived function. I'm going to draw the derivative, which is dy by dx. Okay, so again, this is a number line for gradient. 0 gradient occurs at the start, then occurs at pi, and then it occurs again at 2 pi. Okay, and then what's happening between 0 and pi? What we can see is that the curve is going down the way. It's got negative gradient, so it's going to be in this area. And between pi and 2 pi, it's positive, so that's going to be in this area. Okay, and then the natural path for that to go through then is this. Now what you should extract from that is that's actually a reflection in the x-axis of sin x, which is bringing in a wee bit of graphs of functions. So that means that that blue curve there is y equals minus sin x. So when you differentiate cos x, you get minus sin x, also given to you in the formula sheet. Okay, let's do some examples then. When you differentiate sin, you get cos. When you differentiate cos, you get minus sin. So we're going to differentiate a bunch of expressions here. So let's first of all go for f of x equals 7 sin x. Okay, differentiate sin x, you get cos x, so that's dead straightforward, 7 cos x. Okay, b, y equals root 3 sin x. Okay, you differentiate sin x, you get cos x, so it's going to be root 3 cos x. Okay, part c, we're going to differentiate minus 3.1 cos x, so you differentiate cos and you get minus sin, so that will be minus 3.1 sin x. Okay, question D. (5.9 cos x), you differentiate cos x, you get minus sin x, so that will be minus 5.9 sin x. Okay, question E. So remember, you differentiate sin, you get cos, you differentiate cos, you get minus sin, so what about minus 5 cos x? So if you differentiate cos, you get minus sin, so if you differentiate minus cos, you must get plus sin, so it'll be 5 sin x. Okay, the next one, minus root 3 cos x, differentiate sin, you get cos, differentiate cos, you get minus sin, differentiate minus cos, you get plus sin, so that will be root 3 sin x. Okay, now what we can start to do is just extend that into trigonometry and non-trigonometry. So let's go for this one. We're going to start with y equals 5 sin x plus 3x squared minus 9. And if we differentiate it, we differentiate sin, you get cos, so that will be 5 cos x, and then I just differentiate this as normal, plus 6x, and if you differentiate the constant, it disappears. Final answer. Okay, next one, f of x equals root 3 cos x minus x to the minus 5 plus pi. Okay, so you differentiate sin, you get cos, you differentiate cos, you get minus sin, minus root 3 sin x. Okay, bring this down, minus 5 times that minus will give me plus 5x to the minus 6, and then I differentiate pi, it disappears. Okay, and what I could do at this point is I could tidy that bit up and write it as, bring that back down, 5 over x to the positive 6. Okay, question I. We're going to differentiate minus pi cos x minus the 4th root of x cubed. Okay, so we differentiate sin by cos, but I think we need to do a wee bit of preparation first with this bit, and then differentiate all in the one go. So let's just stick with the original function here and prepare that second term. So that's going to be x to the minus x to the 3 over 4. I'm now ready to differentiate. Differentiate sin, you get cos. Differentiate cos, you get minus sin. Differentiate minus cos, you get plus sin. So that's pi sin x. Then bring the power down, multiply, take 1 away from the power, minus 3/4 x to the, right, so it's 3/4 take away 1, which is 3/4 take away 4/4, minus 1/4 x to the minus 1/4. Okay, and then I can tidy that up. So it's going to be pi sine x minus 3 over 4 lots of x to the positive 1/4. And the final thing that I could do there is reintroduce the root symbol. And that's going to be pi sine x minus 3 over 4 lots of the 4th root of x. Final answer. Okay, let's extend this a wee bit further and start to look at gradients and equations of tangents. So let's go for an example 2, where we're going to find the gradient of the tangent. To the curve y equals sin x plus cos x at x equals pi over 4. Okay, so gradient of tangent first of all tells me to differentiate the thing. So differentiate sin x, you get cos x. Differentiate cos x, you get minus sin x. Okay, I'm now interested in what's happening at x equals pi over 4, so I'm going to have to lean on my exact values knowledge now. So let's sub that pi over 4 in, so it's going to be cos of pi over 4 minus sine of pi over 4. Okay, remember that pi over 4 is 45 degrees, that's your table of 15 exact values you're thinking about now. So cos pi over 4, cos 45, that's 1 over root 2, minus sine pi over 4, that's sine 45, that is also minus 1 over root 2, so it's 1 over root 2 minus 1 over root 2 to give me a final answer of 0. Okay, let's push on and look at some equations of tangents. So we're going to find the equation of the tangent to the curve y equals 1 plus cos x at x equals pi. So this time we're looking for the equation of the tangent this time. Remember that tangent is a straight line. So what I'm going to need then is point and gradient. How I'm going to get the gradient, differentiate the function. Okay, a lot of similarities to your unit 1 stuff. Okay, I differentiate 1 and it goes. Differentiate cos x to get minus sin x. I'm now looking at x equals pi. So that'll be minus sin pi. Okay, so remember that pi is 180 degrees, so sine of 180, well, sine of 180 is equal to 0. So minus sine 180 minus sine pi, well, that's also 0. Okay, so I've got a gradient, now I need to find my point. Okay, so I've got the x-coordinate is pi, and now I need to find the y-coordinate. How am I going to get that? Sub it into the original function for y. So y equals 1 plus cos pi, and then cos pi, cos 180, let's have a think about that. That's down here, that's minus 1, so that's 1 minus 1, and that's equal to 0. So I've got my point, and I've got my gradient. Okay, now think about the gradient here, it's 0, which means I've got a horizontal line. Now think about what you know about finding the equation of a horizontal line. What we know is it's just going to be y equals something, and it's just where you cut the y-axis, which is 0. Okay, next question is as follows. We're going to use differentiation to show that the function f of x equals 5 sin x has a maximum turning point at x equals pi over 2 of 5. And at min at x equals 3 pi over 2 at minus 5. Okay, so turning points, well, that's stationary points, differentiate the thing and make it equal to 0. So again, it's using a lot of your skills from Unit 1, but bringing in the trig element now. So differentiate 5x to get 5 cos x, make the thing equal to 0, and then explicitly state stationary points occur when f dash x equals 0. Okay, so 5 cos x equals 0, cos x equals 0 for 5, and cos x is equal to 0. I can now sketch a cast diagram. I'm going to be in the all quadrant and the cosine quadrant. So x equals cos inverse 0. Okay, so what's my exact value for that? That is pi over 2. Okay, now that's my all quadrant solution. I'm also in the cosine quadrant, which is going to be 2 pi, take away 3 pi over 2, take away pi over 2 rather. So think about 2 pizzas, take away half a pizza, will leave you with 3 halves, 3 pi over 2. Okay, right, so I've proven that I did indeed get pi over 2 and 3 pi over 2 as my x coordinates. I now need to establish the y coordinates, so I get that by subbing back into the original function. Okay, so let's first of all do pi over 2 back into the original function. So the original function is in functional notation, so it's going to be f of pi over 2 is equal to 5 sine pi over 2. Okay, sine pi over 2 is sine 90, that's 1 times that by 5, and I get 5. Okay, that's what I was looking for. Now let's try a substitution of 3 pi over 2. 5 sine 3 pi over 2. Okay, so that's going to be 270 degrees, 3 pi over 2, and that's minus 1. So let's have a think about that with the cast diagram as well. So 0, 90, 180, 270, 3 pi over 2. Okay, so I'm in the tan quadrant, so sine is going to be negative. The angle in there is 90 degrees, pi over 2, minus sine pi over 2, minus 1. 5 times minus 1, and that is minus 5.